Latella, and I'm the coordinator of the COMMECT project. I will shortly start this webinar with an introduction about the project for those that are not familiar with it. And after I will hand over to the two speakers of today's webinar, Alia Bolovic from Luxembourg Institute of Science and Technology and Valtteri Maninen from COMMECT in Finland. And they are our LCA expert, and they will present the results of the environmental impact assessment in the living lab. So let's start now with some housekeeping rule. Next slide, please. So before we go into the detail, I would like to inform you that we are recording this webinar. It is mainly for our dissemination purpose. We will share the webinar in our the recording in our project website. We hope that's fine with you. And please keep your camera off, and we will also keep your microphone muted. But feel free to share your question in the Q&A chat. We will take the question at the end, and you are also welcome to raise your hand in order to have a more interactive discussion. Thank you. So let's start talking about COMMECT. COMMECT is a Horizon Europe project that started almost 3 years ago. We are moving toward the end in August, and it was a 5 million project that was funded in the cluster 6 with focus on connectivity solution, edge solution for rural area, remote farming and forestry. As the acronym explain, we are looking at rural community and how we can connect them. So the main objective of COMMECT is to try to reduce the digital divide, because unfortunately it is still a reality that rural areas are disconnected compared to urban one, but we need to make sure there is connectivity and there is a network infrastructure, because otherwise the rural community cannot have access to digital tools. So to support the rural community in the digital transition, we have first of all to make sure there is a network infrastructure, a connectivity solution that can enable new digital application for smart forestry and agriculture. COMMECT has adopted a bottom-up approach based on the living lab methodology. So in COMMECT, we created 5 living labs. These living labs are distributed in and across Europe, and each of them focus on a different sector. So viticulture in Luxembourg, livestock transport in Denmark, forestry in Norway, crop monitoring, sustainable agriculture in Serbia, and olive tree farm in Turkey. In all these living labs, we have investigated different type of connectivity solution that include terrestrial network, but as well non-terrestrial network like satellite, drone. And in each living lab, it was clear that there is a need of extending the coverage in order to enable application that can support, for instance, microclimate monitoring. This was common in Luxembourg and in Turkey, and that can help situational awareness in forest, or can help monitoring the pig during the transport and during loading and unloading operation. Well, COMMECT did not only focus on the design and developing of connectivity solution, but also performed environmental impact impact assessment analysis, and we wanted to understand, okay, what is the impact of adding network infrastructure, installing devices in the field? Can these have a positive environmental impact? How and in which way? And today the webinar will present the methodology that has been adopted and as well the results obtained in 3 of our living lab, in particular Luxembourg, Turkey and Serbia, that are all focused on crop monitoring, and I leave the floor to Valtteri.
Thank you, Maria-Rita. So, my name is Valtteri Manninen and I am from Seinäjoki University of Applied Sciences, and I'm working as a LCA expert in this COMMECT project. So first I will tell you about LCA methodology shortly in general. So in a nutshell, LCA or life cycle assessment is a method to study environmental impacts of the research subject during its whole life cycle, starting from raw material extraction and ending to end of life, or through recycling back to raw material phase. LCA can be done also for selected part of the complete cycle. LCA is standardized method by these ISO 14040 and 44 standards, but a large group of more specific standards and guidances exist. With LCA, it is possible to evaluate many different environmental impacts, and several different life cycle impact assessment methods exist. In COMMECT, we are using EF version 3.1 no-LT method, which includes 16 different impact categories, including, for example, acidification, climate change, euphorification, human-toxic and particulate matter formation. And as a voluntary part of LCA, results from different environmental impact categories can be combined with weighting and normalization methods to a single value. In COMMECT, we are using European Commission recommendation for weighting and normalization approach to form so-called AF score value. And next, I will tell you about LCA's 4 main stages. So LCA is divided into 4 main phases. So first one is goal and scope, where system boundaries, functional unit, and specific methodologies and tools are defined. Second one is inventory analysis, which is for gathering relevant data, categorize life cycle phases, and identify background of the study. Third phase of the LCA is impact assessment, where inventory items are converted into environmental impact via characterization methods. And finally, fourth and last phase of the LCA is interpretation, which includes dataset quality evaluation, identifying potential trade-offs between different impact categories, and draw conclusions and recommendations of the study. So next about LCA methodology in COMMECT specifically. So with basic ISO standards, ETSI and ITU standards were used as complementary guidelines in COMMECT methodology. Due to these guidelines, environmental impact assessment is implemented like it is defined in this figure. Effects are divided into first order and second order effects. First order includes production and use phases of connectivity devices, and second order effects include indirect environmental consequences of adapting digital solutions, for example, decrease fuel or pesticide consumption. Second order effects are divided into 2 parts, reference case on right side and case with implemented connectivity solutions on left side. With this equation, first order effects minus change in second order effects contribution of the connectivity solution is defined. So about scope and scope in our assessment. In COMMECT project environmental impact assessment, there was 2 main goals. First, to evaluate whether the connectivity solutions have contribution to climate change mitigation, And second, see if there are significant trade-offs with other sustainability indicators. In other words, determine potential to decrease climate change impacts with the selected connectivity solutions, and see if other environmental impacts increase at its expense. Our agricultural processes look at both 1 kilogram and 1 hectare based functional units. This is because yield can play a big role, and since we do not have long-term longitudinal data, we found this to be most appropriate way to go. Then about inventory analysis phase of farming activities. So data collection in COMMECT assessment was planned together closely with Living Lab representatives. Data was collected basically over 2 years, first in 2023 without connectivity solution to get data for second order in reference case, and after that in 2024 with connectivity solution for second order with connectivity solution, naturally. Main farming activities were defined to get data from the processes which most likely have contribution to environmental impacts. These slightly differ between living labs, but basically there was pest and fertilizer application, maintenance and irrigations, and etc. And here is an example of data collection template we prepared for Living Labs. This one is for Living Lab Luxembourg, but template is quite similar for each Living Lab. So with same template, we collected data from first order effects and second order effects. And next, Alia will continue about inventory analysis of the connectivity solutions and Living Lab results.
Wonderful. Thank you, Valtteri. My name is Alia Bolovic, and I'm an engineer at the Luxembourg Institute of Science and Technology. As a part of my role in the COMMECT project, I developed a life cycle inventory, or LCI, of different connectivity solutions applied throughout all the living labs. So to do so, I collected information on the devices used in each living lab and researched the main components and materials that make them up. This was done mostly via peer-reviewed research, but also looking at manufacturer descriptions of the products. And the inventory includes both the production phase of the connectivity solution and the use phase of the connectivity solution. So this would be the power consumption required to keep it running, also the kilowatt hours or electricity needed for data transfer in this connectivity solution, as well as battery types or lifetimes of batteries. Next slide, please. So now we will go into the LCA results for the living labs for Luxembourg, Serbia, and Turkey. So for the Luxembourgish living lab, the use case we evaluated was related to the in-field microclimate and crop monitoring. We wanted to assess if these connectivity solutions allowed for a reduction in overall emissions due to more precise agricultural activities. So we evaluated, like Valtteri said, for 1 kilogram of grapes and 1 hectare. And on the right, we can see the system boundary of our studied system. So in red are the connectivity solutions that were implemented in the second year, so in 2024. And in green are the flows that we believe actually may change as a result of these connectivity solutions. So hopefully we reduce pesticides, fertilizer, fuel, etc. And as main agricultural activities, we considered pest control, fertilization, and field operations with the tractor. So mowing, canopy trimming, spraying, etc. So for the life cycle inventory, this comprises the connectivity solutions that were used. So this was a weather station, a soil station, and a LoRa gateway. Additionally, we evaluated 10 pesticides and 1 fertilizer, 7 different tractor activities, and also uniquely in this living lab, we had no irrigation. The vines were actually rain-fed, so we didn't need to include that in our system. Next slide, please. So when we look at the climate change impacts of connectivity solutions, these would be the first order effects. We can see they're rather dominated by the production phase. The weather and soil stations are powered by battery, and the LoRa gateway is actually powered by the Luxembourgish electricity mix. So to clarify that these connectivity solutions were just implemented in 2024. Next slide, please. So first, before going into the results of the overall results, I would like to just make a mention about the yield. So 2024 was actually an incredibly rainy year here in Luxembourg. It rained probably until mid-July. So we actually had a reduction in yield by about 20%, and we will see how this plays out in the results going forward. Next slide, please. So first, I will show the climate change impact of pesticide and fertilizer application. So as recommended by the environmental footprint methodology that Valtteri mentioned earlier, we should only include active compounds that are in a pesticide. So that's what we did here. And we can see that overall, we had to use a little bit more pesticide in 2024 than 2023. And that's because of the rains, because we had to make sure that our vines didn't get contaminated with mildew. So next slide, please. And now we can see the climate change impact as a result of tractor activities for year 2023 and year 2024. Overall, we had one additional mowing activity and 3 additional spraying activities, which is why we see a higher jump in those categories. The activities where there's only a slight increase from 2023 to 2024 is because of this reduction in yield, since we're evaluating the impact, the climate change impact per kilogram of grape. Here's where the yield really makes a big difference. So next slide, please. Now we evaluate the total impacts of agricultural activities. So this considers the first order effects and the second order effects. And this was calculated with the equation that Valtteri had shown earlier. So overall, we see an increase in impacts. But again, this is because our second year, year 2024, had higher impacts overall due to this decreased yield. So this trend was true for all impact categories. Shown here is just climate change and ecotoxicity impacts. However, I should mention that when we look at the relative contribution of connectivity solutions to the overall agricultural activity in the Luxembourgish Living Lab, we can see that the share is very low. So 1 to 3% for climate change, 2 to 9% for water use. And I will address this further actually in the next slide. So next slide, please. So in considering the results from the last slide, the influence of a reduced yield led to increased impacts from pesticide application and tractor activities, mostly due to spraying. So we cannot fairly say that the reason our impacts increased overall is because of connectivity solutions, particularly that we see across the board. They account for a very, very small percentage of the overall impacts. So what we would recommend is actually to look at a longer time frame to perhaps get an average, maybe average values over 5 years. That way we can account for and negate these unfavorable climatic conditions that we might experience when looking at the influence of an ICT or a connectivity solution. So now we will move on to the Serbian Living Lab. Next slide, please. Yes, thank you. The Serbian Living Lab contained several use cases where different connectivity solutions were implemented. So we evaluated the use case that related to a shared agricultural platform to see if this encouraged farmers to farm more precisely and reduce emissions, because this was the culmination of all the applied connectivity solutions in the COMMECT project. So like Luxembourg, we used both per kilogram and per hectare functional units. And on the right, we can see the system boundary of our studied system. So in red are the connectivity flows, connectivity solutions that were implemented in the second year, and in green are the flows that we believe may change as a result of these connectivity solutions. Additionally, in 2024, Serbia implemented a mobile solar generator, which was a tractor with 30 kilowatt photovoltaic panels to power the irrigation and connectivity devices. And we will discuss this a bit further in the results because we will see how this actually influenced the overall results for Serbia. Next slide, please. The Serbian Living Lab contained several different crops. So we evaluated on a per crop basis and in total. There were quite a few connectivity solutions implemented here, as you can see in the diagram. This ranged from cameras to LoRa gateways, GPS trackers, and different sensors. These solutions were all powered by the mobile solar generator, or the MSG, as I may refer to them. And additionally, we did not have any specific pesticide information, so we used a generic pesticide, and the tractor was mostly for spraying operations. Additionally, we had 2 different irrigation systems depending on which crop we were evaluating. So next slide, please. Here we can see the relative contribution of the agricultural processes per hectare for the soybean crop in 2023. This did not have any connectivity solutions, just to clarify, for 2023. We can see that fertilizer production is the primary driver of impacts across the board, followed by the use of irrigation. And this use of irrigation is because of the diesel that needs to be burned to irrigate. So this is where we'll see that change in 2024 because of the influence of the mobile solar generator. Next slide, please. Here we can see the relative contribution of different connectivity solutions on a per kilogram basis for one of our onion fields. So this is just to give an idea of how we can look at impacts in LCA. And what we can see here is the switch is the most impacting of all the impact categories, followed then by the EdgeML kit and the camera. Next slide, please. So here are the total results for the Serbian Living Lab, including the connectivity solutions. These values were calculated using that equation that Valtteri had showed previously with the first and second order effects. So like I mentioned earlier, the mobile solar generator reduced by about half, actually, in some cases, the overall impacts. So what I did instead was I looked at, okay, what is the reduction in impacts with the mobile solar generator, and had we not included a mobile solar generator, what would have been the following impacts? So on a per kilogram basis, we see a slight reduction overall. I didn't show it in this presentation, but we did also have a slight increase in yield from 2023 to 2024. So that does play a role. But like the Luxembourgish Living Lab, this study could also benefit from using average data over several years to then understand the connectivity solutions. So on the right, the 2 rightmost columns is where we see the per hectare or per kilogram if we had not implemented a mobile solar generator. But then we can see quite a lot of impact actually in the 2 middle columns when we include this mobile solar generator. Next slide, please. So to conclude for Serbia, switching the use phase of irrigation from diesel to solar power yielded quite a hefty reduction in our impacts overall. And again, like the Luxembourgish Living Lab, the connectivity solutions actually remained a very, very small percent overall. So generally 1 to 3% for all impact categories. We didn't find any substantial trade-offs either when we were looking at the influence of connectivity solutions. So that means we didn't find that maybe we reduce climate change, but we augment ecotoxicity. We didn't find such a big difference indeed. So now I will pass the baton to Valtteri so he can discuss Living Lab Turkey.
Thank you, Alia. So next I will tell you results from Living Lab Turkey Smart Olive Tea Farming. So in this Living Lab, two separate use cases were combined to same assessment. And this was done because use cases use partly same connectivity devices and they are affected in the same area. So separating environmental impacts to both use cases is in a reliable way is quite impossible. Living Lab is divided into 3 locations, Izmir, Antalya and Mersin. With minor differences in devices and agricultural activities, connectivity solutions are implemented in the same way. And kilogram and hectare-based functionalities are both used in this Living Lab. Hectare-based is the main approach due to problems with uncertainties in the yield because of short time frame of the data collection. And however, with additional data from second olive farm in Izmir location, we were able to collect data from corresponding olive farm. So data collection was possible to do in the same year, in the same location, and with same growing conditions. So only difference between these 2 olive farms in Izmir was COMMECT connectivity solution. And in this way, it was possible to make LCA with kilogram-based functionality in this case. So Turkey's connectivity solutions is 2 separated solutions which both aim to notify end users on the most effective control type for diseases and pests and so support environmental sustainability and increase yield and quality of the product with the right, timely and adequate use of pesticides. So first solution, Microclimate monitoring for early disease and pest detection, aims to provide olive farmers with early warning systems that work with accurate algorithms using climate stations and related software and to optimize treatment timing and doses for olive ring spot disease control. The solution involves installing climate stations in olive yards, and these stations collect high-resolution data which is transmitted to our remote server, and the data is then processed by decision support platform. This approach helps olive farmers apply plant protection treatments more accurately, reducing unnecessary spraying. And second solution is monitoring of pest insect traps, aims to provide olive farmers with digital traps that work with pheromone and food, and to optimize treatment timing and doses for olive fly. The solution involves installing digital traps in olive yards. These traps collect high-resolution photos, which are transmitted to remote server, and the photos are then sent to the decision support platform. This approach helps olive growers apply plant protection treatments more accurately, reducing unnecessary spraying. In the figure here, you can see what kind of devices solutions use, for example, weather and soil stations, insect traps, data and signal processes, etc. And like I mentioned earlier, from LCA perspective, we are considering these two solutions as one. So I will start with our main results. So here you can see our climate change impacts per hectare in 3 studied locations. There are 4 columns per each location. First column, FO, means first order effects or impacts of the connectivity solution. Second column, SO, CON, is second order with connectivity solution or farming activities with connectivity solution. Third column, SORF, is second order effect without connectivity solution. And fourth column total is first 3 columns combined, like stated in the methodology that I showed you earlier. So shortly, negative total value indicates that climate change impacts are decreased due to connectivity solution, and positive that they increased. So few points you can see from this figure are that first order effects are much smaller compared to second order effects. Total value is negative in Izmir and Antalya, but positive in Mersin. In this context, it is important to notice that olive farms area is different in each location, and magnitude of total value seems to be connected to the size of the area. This makes sense because connectivity solutions are quite same regardless of the area size. Antalya values are much lower overall, but that is because some farming activities were not used there that were used in Izmir and Mersin. And next you can see chart of the relative contribution of the agricultural processes to all 16 environmental impact categories we modeled. This is an example from Izmir location with connectivity solution, but results were quite similar in each location. Main things to notice are that the most of the contribution is in almost every category were done by fertilizer production and use of diesel-powered machinery, which means basically tractors. Also, one of the two pesticides causes some impact in 3 categories: ecotoxicity, non-carcinogenic human toxicity, and ozone depletion. And in next chart, you can see very interesting results from 4 most important impact categories. These 4 categories, climate change, ecotoxicity, non-renewable energy resources, and land use, were selected based on the weighted and normalized EF score values, which indicated that these categories formed over 99% of the total EF score. This chart shows you relative change in per hectare results in these categories after implementation of the connectivity solution. So you can see that change is negative in all 4 categories in Izmir and Antalya locations, but some values are positive in Mersin location. This means that there are some trade-offs between impact categories in this Mersin case. And next chart looks quite same as previous, but this is now from Izmir location from additional analysis. This means that these results are kilogram based, and so they take into account increase in the yield. Compared to last result, it looks pretty much same, but now change is much higher. In last slide, relative change in climate change impact in Izmir was about 2%, and here it is almost 30%. So changes in the yield have very substantial meaning to environmental results. So, as conclusions from Turkey, environmental burden decreased in Izmir and Antalya locations without substantial trade-offs. Anyway, burden increased in Mersin location and trade-offs were found, but due to functional unit, yield was not considered and area was rather small compared to other locations. So we can say that these Izmir and Antalya locations were in some way more reliable. And changes in the yield have significant impact on the environment. So if connectivity solutions does not have positive impact to the yield, or yield is not considered in assessment, impacts remain quite minor. And third point, the connectivity solutions is more environmentally effective on larger olive farms, and this is based on the results from smallest farm in Mersin compared to other farms. And there was our 3 cases we were presenting today, and overall conclusions are these that connectivity solutions have only minor environmental impacts in comparison to agricultural and rural activities. All presented solutions have potential for climate change mitigation, and no significant trade-offs between impact categories were basically found. Especially in agricultural context, it is crucial that connectivity solutions lead to increased yields to achieve substantial environmental benefits. It is also important to notice that this assessment does not take into account increased quality of end products. That is the case with some connectivity solutions, And lessons learned from this project and assessments are that we recommend using longer-term longitudinal data in this kind of studies. However, in this kind of project, it might be challenging to collect data from multiple years. Also, it is beneficial to complement LCA with other assessment methods. For example, in COMMECT, socioeconomic assessments were implemented in living labs together with these environmental assessments. And last thing I want to say is that close collaborations with living labs is very important in this kind of assessments, as it is essential for practical implementation and validation. And in my opinion, we succeeded in this during the project. Thank you, and I think now we will move to Q&A session.
Thank you so much, Ayla and Valtteri, for your presentations. I'm Gabriel Linton. I'm the dissemination work package leader. So I will host or facilitate the question and answer session here. So if you have any questions, feel free to raise your hand or post your question in the Q&A button, which is a separate button next to the chat function, and we will see if we can get some questions and see if we can get a discussion. So if you have any questions, feel free to post them or raise your hand.
Maybe while we give some time to people for writing, I would like to thank again Alia and Valtteri for their work, and as well the member of the Living Lab that have supported this work, providing the necessary information, because without data the LCA analysis was not possible. And linked to this, I was wondering, well, we applied this in our living lab, but do you think that the same methodology could be easily adapted to apply to other living lab from other projects, because they may have different use cases, but more or less, let's say, some common aspect with our system?
Yeah, I can answer to that. So I think it's of course possible to implement this kind of methodology in other similar use cases. Of course, some use cases might be a bit harder to implement, but mostly it is quite possible, and even we hope that these kind of assessments are doing in future projects.
Good. Thank you. And we got a question here in the Q&A. And it says, thank you for a great presentation. Could you please elaborate on the negative impact numbers for Serbia Living Lab on slide 27?
Yes. Thank you, Mikael, for the question. I don't know if Valtteri, we can go back to slide 27, but if not, I think I know which slide you're talking about here. The negative impact values are the total impacts after we consider first order and second order effects. Now, again, in the first two columns that have values, including the MSG, we say negative values, but most of this is actually attributed to the MSG, because here we replaced irrigation by diesel with irrigation by solar panel. So we had a very substantial drop. So when we looked at then the result from 2023 and 2024, so actually it should be 2024 minus 2023 according to the equation, this is where we get the negative value. And we see this for both the per hectare and per kilogram values. Now, when we look in a hypothetical situation that the MSG did not take place, we see this for some impact categories for the per kilogram, also because we had an increase in yield. for 2024. So on a per kilogram basis, we'll see that we had negative impacts, but it's also because of our yield. So then when we look at the per hectare, we actually have some positive impacts because we did not replace diesel. And in other cases, the inventories actually were relatively similar from year 2023 to year 2024. So on a per hectare basis, we won't see as much this change. I hope that answered your question. Okay, seems like it did.
Yes. Thank you very much for that question and answer.
I have an additional question, if I may, because let's say I have the interest in the LoRa technology. It is very well like advice for application in agriculture because it is low power. But let's say in your analysis, were you able to really quantify the impact, for instance, of a LoRa gateway? Because you presented the global results, but if we want to look into a specific solution and a specific device, would you be able to elaborate a bit more on this?
Yes, I can take this question. Thank you, Marie-Rita. So yes, you can with LCA look more specifically into a certain device. So it's true that here we gave an overall because we're limited in time and it's a webinar, it's not the right format to go so deep. But you can actually break down a LoRa gateway into say that we have a cable, we have an antenna, we need to have a power over Ethernet, we need to have certain other connectivity components, so a motherboard, integrated chips, etc. And then even from there, you can actually see where's the impact coming. So you can actually go several tiers up in LCA, which then gets quite interesting and actually maybe gets out of the scope of the COMMECT project, because then you can actually figure out what materials really are the main contributors. So for example, I know in digital devices, gold is a very, very big contributor to climate change emissions. So that could be then for somebody in another project, maybe a material scientist working to say, how can we replace gold conductivity to make the actual device itself less carbon intensive, if you will. But yes, you can look then in different devices to see exactly what the material components are and also the different use phase. So you could also look, okay, what is the emissions of a LoRa gateway if we use it in Luxembourg versus in France versus in Germany, because the electricity mixes are different. So that's also a possibility with LCA.
Thank you. Very interesting, but as you said, maybe not all the aspects could be covered within our project time frame, but
right.
Thank you.
Thank you. And talking about this time frame, I mean, you have this limited time frame now, and agriculture is very weather dependent, so you have some very big fluctuation. And someone that's not familiar so much with LCA and assessments, how can you work with just having like 1 or 2 years of data? Is there any way you can smooth the data out or make it more comparable?
Yeah, actually one thing we did, because we have so short time frame for data collection, was that we are focusing on hectare-based results and not kilogram-based results, because like you said, these things like weather conditions and etc. have very big contribution to yield, and so these kilogram-based results from different years are not comparable. So that is the reason why we used basically mostly hectare-based functional units.
And how does that help the hectare compared to the kilo?
So because then when we are using a hectare-based functionality, this changes in yield doesn't affect the results. So basically only then the different kind of inputs we are putting in the system are.
Okay. So then you focus on just the inputs into 1 hectare. You're looking at yield at all.
Yeah, when we are using hectare pest functional unit, yes.
Good, thank you. Any more questions?
During the presentation, you both highlighted that where the size of the farm had an impact on the results, and as well the type of crop. No, if I understood well, did you notice any relevant, let's say, results from the analysis in Serbia? Because there were different type of crop that were considered. Did you notice anything relevant to share? Or more or less you had similar results for all the type of crop?
For Serbia, I had different results for the crops, and this was mostly as a function of yield. Because, for example, onions, even though the onions were grown on 2 hectares and soybeans were grown on 2 hectares, the weight of an onion is much different than a soybean. So this is where we see those differences, and this is also when we looked to compare the results with other studies or other life cycle inventory databases. We could actually see the difference as well. So we are still within the range of what we find in literature, but you do see that difference within different crops. Yes.
Good. Any more questions?
So I guess we are in between the time for the lunch for most of the people. And I think we can thank once again the speaker and of course the attendee to join us. And indeed the webinar has been recorded because I just saw this question in the chat and will be shared in our project website, so you can watch it again. Here there are the email of Valtteri and Alia. You can reach them if you have specific question. We have also our project email address for other questions that you may have in general. And maybe we can also take this opportunity to announce our final event that will be on 10 of July in Turkey, and we will be presenting the activity that have been done in the Living Lab Turkey and as well Serbia, and we will be happy if you want to join. It will be an in-person event, of course, to do some field activities, see the actual deployment, and have some exchange with the stakeholder.
Yes, thank you very much to Maria Rita and Valtteri and Alia for your presentations. And thank you for everyone that participated.
Thank you. Bye-bye.
Thank you. Bye-bye.
Thank you. Bye.
Thank you very much.
Thank you.